So let's talk about quantiles, and the problem is the following. So you get a stream of numbers, or actually any comparable item. This could also be documents, like in lexicographical order. And at the end of the stream, or sometimes in the middle, you want to be able to answer questions such as, for item X, how many items are smaller than this X? Right? And if you can answer this question for all X, then this is actually a CDF. Right? That's just the probability distribution of the items that you're seeing. And I mean, I won't get into the motivation. It's just highly motivated, load balancing, a bunch of stuff. And like an easier, like a specific version of this is, what is the median value? Or what is the, I don't know, 25 percentile? So somewhat more formally, you get a stream of capital N items, and you have parameters of epsilon, which is the error you're willing to tolerate. With no error, it's impossible to do this with sublinear space. And confidence delta for randomized algorithms. And you'd like to approximate the function CDF of X, that for technical reasons, it's not normalized. It's the number of items larger than X. And there are two variants of this. One, the single quantile problem, is one where there is some fixed element X, and you're just interested in answering how many elements are smaller than this fixed item X. And for all quantiles, you just reverse the sentence, and you want to just be correct for all possible numbers. And what I'm going to solve is the first one, the single quantile. And just, if you think about it, if you nail it correctly for 1 over epsilon different items, then you actually have the answer for everything, because you have your barriers. So you just need to do a union bound over 1 over epsilon items. So what I'm going to measure is, so the running time, the update time is, I'm not going to talk about it because it's going to be easy, but the space is what needs to be optimized here the most, and I'm going to just count the number of items that I store. I'll ignore the space needed for counters. I mean, there's no cheating, there's no counters that can take too many values. And finally, another property that is desirable is that the sketch is mergeable. And non-formally, this means it can be applied in a distributed environment. So just a bit more about mergeability. It took me a while to figure this out completely. So usually when you think of streaming, at least for me, I thought of, you have a single machine, there's a sketch, you initialize, you see the items, you update, and at some point you get a query and you need to answer it. But if the stream is so large, then what usually happens is that you have a lot of machines that deal with it, and each of them has their own sketch, and they update it all the time. Sometimes you get a query, they merge. The merged sketch get merged, and there's a bunch of merge operations, and you want the properties. No matter how many merge operations there were in the middle, you get the same quality as if there was a single machine. And it doesn't always come for free, this property. Okay, so there are more works. I'm just giving some highlights. First one is kind of the first thing you could think of, which is a random sample. And it works, but you need 1 over epsilon squared items for this to work. And as it turns out, you can be linear in 1 over epsilon, which is also a trivial lower bound. And the first notable sketch is by MRL, and I'm noting it just mostly because I'm going to use a lot of their techniques. Then there's GK, Green-Rocana, this GK sketch. I'll refer to it later. It's, as far as I know, this is the best deterministic sketch. And it does depend on the length, again. And then there are randomized versions. Febel and Slopsky, in some non-trivial way, they feed a random sampler into a GK sketch and get 1 over epsilon. The bad thing, the thing is the GK sketch and Fabel-Solvsi are, as far as I know, non-mergeable. That's somewhat of a disadvantage. And finally, there's a paper about called mergeable sketches by Agarwal et al., and they achieve 1 over epsilon times log to the 1.5 of 1 over epsilon. And these are all in a comparison model, meaning you can only compare items. So you can think of other assumptions. So if it's numbers, you can do gradient descent. And if the universe is fixed, for example, then you can depend on the number of items that can possibly appear. And then you can have like log of u, which is the size of the universe. Also, if the items don't arrive in random order, if somehow you know the data is shuffled, then something like gradient descent, which actually can be extended to any comparable items, can be done, and you can get a sketch of 1 over epsilon size, but it only works for epsilon, which is larger than 1 over square root of n. And finally, there's a non-trivial lower bound for deterministic algorithms. And this lower bound applies not only for the all-quantile problem, but also for the single quantile problem, which is the easier version. You just want it to do it directly for one number. And, well, actually, it's deterministic. So as it turns out, for randomized algorithms, this was somewhat surprising. At least you can do better. You can be, like, the 1 over epsilon is required, but the probability of failure can actually be doubly logarithmic. It could be, like the complexity is doubly logarithmic. So this is what we achieve. There's also a lower bound for the randomized algorithms, and so if you don't care about mergeability, then the upper bound matches it. If you do, then we need this log square part. And then again, all quantiles is achieved by a union bound. And it'll be nice to see if it can be avoided. That's in the end. So the key component that we use is something that was used by the MRL sketch, and that is called a compactor. So the way to think, this is a kind of a different point of view than what I was used to. And think of it as some item that gets an input stream of length n, and all it needs to do, it outputs a stream, but the length of this output stream is n over 2. And if somehow you made sure that the error you entail, meaning the function for this stream is somewhat similar to the function of this, meaning you suffered an epsilon error, then you can just concatenate a bunch of these, and after log n many sketches, you have something that you can just store. Right? So let's see what this compact operation does here. So you basically have a buffer, and you see items in the stream, and you see more and more until you reach your cap, which in this case is 6. So I have my 6 numbers. Now I sort them. I pair them into blue and red numbers, and I just output either the blue ones or the red ones. And this is the output stream. So now again, I see more numbers, I reach my cap, I sort, I pair, and I output more. And as you can see, for every 6 numbers, I output 3 numbers, so I have the number of the sketch, the size of the sketch. And the useful thing about this is that after a single compact operation, my answer did not change by more than 1. And why? Think of some number x. Let's say it's here. Then in the original streams, there are 3 numbers smaller than it. And after I do this compact operation, the number of items I'm going to guess are smaller than it is either 2 or 4, depending on whether I chose the blue or red items. And this is even the bad case, because if I'm lucky, like y is in an even position, and then I just suffer no error at all. Okay, so that was one compact operation. Let's talk about the first compact stream. So in the first compact stream, I see the numbers and I perform these compact operations. And if I chose a capacity of k, which is some parameter, then the number of compact operations I'm going to do is n over k. Why? Because every k items is one compact operation. So total number of n over k operations, each one of them gives me an error of 1. So in total, this gives me an error of n over k. But this is a worst-case analysis, and if you think about it, at least for the first layer, this is a really bad approximation, because if you chose the items blue or red at random, then this error, this difference, is a sum of signs. It's a sum of n over k random signs. And this thing is really a sub-Gaussian with mean 0 and a variance of n over k. And this would typically be square root of n over k, which is much lower, at least for large streams. So given this in mind, this was the analysis for what happens when I have the initial stream n to n over 2. And like analogically, you can analyze the error you suffer from height h to h plus 1. And like the difference is n divided by 2 to the h because the stream is shorter. But really, I need to scale things up to match the original weights of numbers. So I need to multiply everything by 2 to the h. And so the variance gets multiplied by 2 to the h square, and this is the new variance of the sub-Gaussian, 2 to the h time n. So the more I climb, the higher my variance. Initially, it's like you do the sum, a telescopic sum, and it's just a geometric series. And this is what you suffer. This is where the analysis of Gawal et al. Ends. And this gives you a sketch of log epsilon n times square root of log 1 over delta over epsilon. But now, when you look at it this way, you notice that we had some looseness in the lower terms, or in the first sketches, like we basically suffered no error. Like in the first stream that gets n items and outputs n over 2, our error was unbelievably small. So we could actually use a much smaller capacity there. And the formal thing is you can actually have like the capacity for layer number h could be the parameter k times 2/3 to the capital H is the last layer and small h is the current, so 2/3 times h over h. So you have this geometric sum, and you do the same math. I won't get into the details, but you end up losing basically nothing, just a constant, 3 times this instead of 2 times this. But then the space you required is not this k parameter times all of them, but it's a geometric sum. And naively, you'd still need something to do with log n, because there are log n many layers, and each of them requires constant memory. You can't do less than 2 items. But all of these compactors that have 2 items in them, if you think about it, what happens when you have 2 items? You get 2 items, you sort them, and then you sample one of them at random. So it doesn't, I mean, the sorting was useless. You just picked a random item. So if you have like, I don't know, D of these concatenated, then what you're actually doing is picking 1 item at random out of every D items, out of every 2 to the D items. And that can be implemented with basically 1 element, with reservoir sampling. Right, so that's a less formal but graphical way of viewing the algorithm so far, is that you have some sampler that samples 1 item out of every 2 to the something items. Then you have a sequence of log of 1 over epsilon compactors. And then this outputs a sketch of size square root of log 1 over delta over epsilon. And we're almost over, but I still owe you a doubly logarithmic dependence on delta. And this comes from the following observation. For the last layers, you have a constant number of compact operations. So for these, like I have basically a sum of, I don't know, 4 random signs. So I don't want to treat a sum of 4 random signs as a sub-Gaussian variable and give some high probability bound, because there is no high probability bound. I need to handle the worst case scenario. And if I'm going to handle the worst case scenario, then I'm actually better off at just giving it the maximum capacity. So oddly enough, what you need is the same thing as before, but the log 1 over delta top compactors should have a capacity of K. And this thing is still mergeable, and it gives you a sketch of size double, like log of 1 over delta squared over epsilon. And finally, another observation is that this box, the only thing I need from it is to give me, I mean, to be able to handle a stream of very small size, log of 1 over epsilon, and output and maintain a sketch. And as it turns out, the algorithm that's best equipped to handle this type of problem is the GK sketch. Because it, like if you give it something in the order of x over epsilon, then the sketch size is log of x over epsilon. And that's how the GK sketch gets a doubly logarithmic dependence on delta. Of course, this is all hand-wavy because I don't know the length of the stream, but these are technical issues that can be dealt with. And finally, the lower bound is also somewhat technical. So we have a lower bound for deterministic algorithms. Just for the due diligence, we can turn this into a lower bound to randomized algorithms. And the way is just to consider a fixed stream size. And if you do that, and you can tune the error probability of your algorithm to be so small that it just performs correctly on any possible stream, because there's only n factorial possible streams. And then you get a deterministic algorithm and the reduction. You get a reduction essentially stating that the lower bound is log of 1 over delta over epsilon. So that's it. Just to summarize, so we resolved the question for a single quantile problem and in non-mergeable sketches. Its 2 possible improvements would be to either show it's mergeable or think of something mergeable that has the same guarantees. And also, this last part of going from single quantile to all quantiles, it's, I don't know, like the intuition says that maybe the union bound is too loose. Maybe you can just prove something. I mean, there seems to be correlations between them, and in a good way, but I guess we couldn't figure out how to get rid of this extra epsilon factor in the log, which is somewhat petty, but you know, it's just closing the gap. And finally, I'm hoping this could be able to be adapted to framer for core sets in general. If you think about this compact thing, it has a bounded error, but the error can be thought of as a number with a mean 0 and variance, basically bound variance. So, who knows? I mean, if you can just fill in this box, then all the other details of the proofs kind of follow. That's it. Yes. It's the lower bound for so yeah, that's, well, it's not a cheat because it's a lower bound, but this lower bound only applies for extremely small delta. Like it could be the case that for, I don't know, for not constant, but sub-constant delta, but not n factorial, you have something, some better answer. Yes.
Even for delta equals to 1 over n, for example?
Yes, I don't know.